Hey guys, here's our notes for Unit 1 about assessing normality, trying to decide if the data that you collected is normally distributed or not. So it's going to go in our slide presentation 16 through 18. At the top of your paper, you can go ahead and put your title, Notes 1.1.3, Assessing Normality. So we're going to look at 3 different ways to decide if our data is normal or not. So the first way you're going to look to see if your data is normally distributed is you're going to use something called the Empirical Rule, which we've talked about before, is the 68, 95, 99.7% rule. What you're going to do is you're just going to go ahead and use your mean and standard deviation to decide if 68% of your data lies within one standard deviation, 95% of your data lies within 2, and 99.7 lies within 3. So you're just going to use the mean and standard deviation to determine if 68%, 95%, and 99.7% of the data lie within 1, 2, and 3 standard deviations of the mean. All right, so let's go do an example of this. So it might not necessarily be 100% exactly those numbers, but it should be close. So your example we're going to look at is in our workbook on page 33. Example number 1 says, the following frequency table shows the cholesterol levels in milligrams per deciliter of 100 randomly selected high school students. The mean cholesterol level of the sample is 165. So the mean is 165 and standard deviation is 20. Analyze the frequency table using the 68, 95, 99.7 rule to decide if cholesterol levels in the population are normally distributed. All right, so what we're going to do is we're going to determine the percent of students within one standard deviation of the mean. All right, so our mean is 165. So we're going to take 165 and we're going to add and subtract the mean. The mean is 20. So 165 minus 20 means we're looking between 145 to, if you add 20, it's 185. So we're looking at cholesterol levels between 145 and 185. So that would be right here from 145 all the way to 184.5 would be these ones right here. So how many people is that? That's 70, right? 70 of them. 34 plus 36 is 70. So out of 100 people, that is 70%. We needed it to be 68, but 70 is pretty close to 68. Then we're going to determine the percent of students with cholesterol levels within 2 standard deviations of the mean. So 165 is the mean, plus or minus 2 times 20. So we're going to subtract 40, which is 125. And then we're going to add 40, which is 205. So ranging between 125 to 205. So 125 would be here, all the way down to 204.5. So it'll be all of these people right here. So all of these people right here, if you add up 15 plus 34 plus 36 plus 11, well, 70, 85, 96. So 96 out of 100 people means 96%. Now we're going to determine 3 standard deviations. So that'd be the mean 165 plus or minus 3 times 20. So I'm going to subtract 60, that's 105. Add 60, that's 225. So between 105 to 225. So that's everybody. Oops. So if we take our 96 we had before, plus our extra 4 people, gives us 100%. Everybody is between 105 to 225. So we look at these numbers, okay, and we decide if we think that it's normally distributed based off of the empirical rule 68, 95, 99.7. So 70 is pretty close to 68, 96 is pretty close to 97, and 100 is pretty close to 99.7. Hypothetically speaking, this was like a 40, a 72, and an 80 or something, then it wouldn't work. Or if this was already at 96, this was 97, and this was 100, then it wouldn't work. But since it's close to the 68, 95, 99.7, then we would say, yes, the distribution is close to the empirical rule. Yes, what is it asked? Is the population normally distributed? So we say, yes, the population is normally distributed. Since it follows the empirical rule. Forgot the P. So it's close to 68, 95, 99.7. All right, let's go look at another way we can decide if data is normally distributed, and that would be looking at it graphically. It says histogram symmetry. Could technically be a dot plot too. Could be a histogram or a dot plot. Either way would work. You're just going to create a histogram or dot plot. To see if it looks symmetric. Or skewed. Also look for outliers. Above or below the mean. So what that means is if you are drawing a histogram, right? Draw histogram. Let me erase one of these. Oops, my goodness. Oh, I want an eraser. All right, so this right here, this little histogram, would have a left or negative skew. Because the majority of the data is over here on the right, but these little values down here on the left are bringing your data, your mean down, so we'd use median. Or if you had a dot plot, and it looks something like this. This would be a right or positive skew. Because these values over here that are not near the rest of the data are pulling the mean up. So let's look at an example of this. So we're going to go to page 34. We're going to do example 2. It says, in order to constantly improve instruction, Mr. Hopple carefully records on how his students perform on exams. The histogram below displays the grades of 40 students on a recent United States history test. The table next to it summarizes some of the characteristics of the data. Use the properties of normal distribution to decide if a normal distribution is an appropriate model for the grades on the test. So here's our histogram. Does our histogram look normal? Does it have where the majority of the data is in the middle and then has a few values on the lower end and the upper end, right? So if I draw my little graph, would that be symmetric, right? Our answer is probably no. So the majority of students are actually doing really well. The majority of students, here's like a 70, majority of students are getting above a 70. And then there is a student who's, got a 0. There's some students that got 40s and 50s, but the majority of students were doing well. So is the data normally distributed? For this test, we would just say no, since the data is skewed. A normal distribution is not appropriate. And this would be a left or negative skew because the values down here are bringing it way down. We're going to skip example 3. We're going to talk about our last way to assess normality, and then we'll do one more example of it. Okay, so let's go back to our little notes page. And our last one is something called a normality plot. So our last one is a normality plot. The way that it works to make a normality plot is we're going to have to use technology to do it. Normally in class, I would give you guys my TI-84 calculator, or I think they're TI-84. And we would use those. I had to try to find a website that would do it because I couldn't figure out how to do it on Desmos. But what you do is you use the z-scores paired with the data to plot points. So it goes data, comma, z-score. And if it's linear, with a line of best fit, then it's reasonable to assess normality. So what that means is we would graph it. Your data goes on the x-axis. Then your z-scores, you could go up 3 in z-scores, or you could go down 3 in z-scores. So that's your y-axis. And then as long as your points look fairly linear, they don't have to be exactly, but if you had a line of best fit that went through them, as long as it looks linear, then we can say that it's reasonable to assume normality. We're going to have to use technology to do this for us. You'll normally use our TI-84 calculators. We're going to use, the website I found was called Math Cracker. And it was just the normal probability plot maker. That will do it for us. Okay, so let's go look at our last example we're going to do, which is example 4. We're not going to do example 3 or example 5. We're going to do example 4 on page 35. It says use a graphing calculator to construct a normal probability plot for the following values. We don't have a graphing calculator. We just have that website that we're going to use. Did the data appear to come from a normal distribution? Okay, so the way that it works when you graph your normality plot, so it'll look like this. Your data goes over here, and then these are your z-scores. So it could go up 1, 2, 3. It could go down 1, 2, 3. So our data is 1, 2, 4, 8, 16, all the way to 32 is our data. I didn't write all of them. But we're going to go ahead and make our normality plot, our normality plot using this website. Okay, so what you do is you go to the website, you can type it in Google, or I can put you guys the thing into Google Classroom, a link to it. But you just type in your data. So my data is 1 space 2, space 4, space 8, space 16, space 32. And then I'm not going to do the name the variable part. I'm just going to go ahead and hit graph it. I thought it would still be here because I just made it when I was practicing. And it took a little while to load then. It's taking a little while to load now. Deleted it. Dang it. Sorry, guys. 1, 2, 4, 8, 16, 32. If it doesn't do it this time, I'll just show you guys what it looks like. All right, here we go. So here's our normality plot. When you look at these points, do they look linear? So when you look at them, they look pretty much like a logarithm curve, like it starts near the bottom and then it kind of curves up, or opposite of an exponential decay curve. So this we would say is not linear. It looks pretty curved. It looks kind of exponential. So we're going to say that it would not be a normal plot. So it kind of looks like this. So it looked like a curve. It didn't look like a line. So we would just say not a normal distribution since it is not linear. Since the normality plot is curved, not linear. So on your classwork homework, you will not actually have to create your own normality plot. The one normality plot question gives you the normality plot. You just have to look and see if it looks linear. Okay? All right, put these notes in your digital notebook and then do some practice.